One way we might try to improve the performance of our sbrk allocator is not call sbrk so often. We could allocate in chunks of 6 words instead of just whatever the application request at a time. And if we do that, then what happens is we start out with nothing, no memory that we've requested from the OS. When the application requests 4 words, then we'll allocate a chunk of 6 words and take those first 4 and give them to the application. If the application then requests 5 words, then we will, we don't have enough space so far, so we'll ask the OS for another chunk of 6 words, and then use the first 5 of what we have after previous allocations for that request, and so on. So you see that we're still ignoring freeze in our allocator, but by the time the application requests 2 words, then we do have space for that, and we don't have to consult the OS. So that is a refinement to the question when or more pages need from the kernel, and that's only when we need an extra chunk to satisfy the current request. To implement this variant of the allocator, it'll be helpful to have a chunk size. Here I'm picking 4 pages instead of just 6 words. And a chunk of line is similar to a line, but for chunk sizes. So let's take that over to our allocator. Let's put it here. That's the size that we're going to allocate sbrk chunks in. And our init will need to set our some pointer that keeps track of where we're allocating currently, and it'll also need to initialize our size back. So the pointer will start out at the current breakpointer, and size starts out as 0. So that replaces init here. And then finally, for malloc itself, after it aligns the size that it's given, it checks whether we currently have a chunk of memory that can accommodate that size. If we can, then we set p to be the current allocation pointer. We increment the allocation pointer by the new size and decrement the amount that we have available for the future, and return that pointer. If we don't have enough, then we ask sbrk for a chunk-sized amount. Actually, at least new size, but aligned to some multiple of chunks. And we can increment our current available size by that much. That replaces malloc. And we can try this out with our checking code, checking driver here. And so far so good. So that's an improvement maybe to our allocator's performance. One benefit of this chunking approach is that it can also work with mmap. So instead of using sbrk, if we allocate pages in some chunks, so I've picked 8 words as the page size here, page chunk size, since that's only 128 bytes, and pages are actually 4096, so realistically we'd pick a bigger number. But it's the same idea. We can allocate, if the original allocation is 4 words, then we would allocate a page chunk and use that. A next request comes in for 5, and well, there's not 5 bytes here, so we still have to allocate another page, and the same for 6. But by the time we get down to this malloc 2 at the end, there is some room in our most recent page, and we can keep using it. So in this case, the question of when do we get more pages, it's not necessarily on every allocation, it's when the most recent page doesn't have any space. We're going to come back to mmap later, but this gives you an idea that we'll be able to do similar things that we're doing with sbrk with mmap in the end. For completeness, here's an implementation. It looks very similar to our sbrk chunking version, except we use mmap and reset current available to the result of mmap every time. At first glance, this naive mmap version might seem worse than the naive sbrk version because we have this empty space. This wasted space, this is called fragmentation. So it's space that we've forced the operating system to map, but we're not using it, the application is not using it as part of its real work. The reason it's not as bad as it looks is that we can just pick larger chunk sizes, and we pick some chunk size that's much bigger than the allocation size, and then the amount of space wasted by mmap is not so much different than the space that we have left over in an sbrk chunk. And furthermore, what we're really interested in, the real obstacle in both of these naive implementations, is that free doesn't do anything. From the application's perspective, that blue block has been freed, and both of these implementations suffer from extreme fragmentation by not reusing this memory, and that means that we need to refine our allocator to keep track of unallocated space.